Physics 2212, Lab 6, Magnetic Molasses. Introduction. The purpose of this lab is to apply Faraday's law to explain the falling of a magnet through an aluminium tube and compare the real observations to ideal ones using both physical experiments and glow script code. Preview of the results. Actual time to drop the magnet was 1.19 seconds, while the simulated time and results was 1.395 seconds. Physics principles. The physics principles we are going to be exploring through this lab are as such. Faraday's law. A changing magnetic field through a loop induces a voltage proportional to the rate of change of magnetic flux. And Biot-Savart law. A steady current produces a magnetic field around it with strength depending on the current. And you can see the equations as shown. The experiment. With one hand, hold the tube vertically and position the magnet just above the top opening. With your other hand, hold the smartphone and get the entire length of the tube in frame on your smartphone camera. We will be dropping the magnet into the tube and measuring the time it takes to fall on average. So this is the procedure for the experiment that we did. And so assumptions that we're making is that there's negligible air resistance. Bar magnet acts as a magnetic dipole. The only forces on the system are magnetic or gravitational. And yeah, that's basically the assumptions we're making. So the initial conditions is that time is equals to 0 and the height of the magnet is above the tube at a fixed point. So the system is the magnet and the surroundings is the tube and everything else. So here are the results. The magnet slowed down as it fell through the tubes, and here is the average time it took to get to the bottom. So here's some of the code. That was the experiment part. Here's the coding part with FlowScript to model it. And so we have our code here. We have the dimension of the tube, properties of magnet, the function calculate the magnetic field, the magnetic dipole, function of calculating time change in flux as magnet falls through the tube. Then we also have some more code here, and we have calculated the force on the magnet from each ring of the tube as it falls through, and we use this along the gravitational force to get the net force acting on the magnet as it falls. And so we continuously updated this to determine how long it takes for the magnet to fall through completely. And so results. Shown is a graphical representation of the data generated by the code. The shape of the curve is determined by the strength of the magnetic field at that point in the tube. It seems that the results gotten from the real experiment show that the average speed is lower than the computational model. Despite this discrepancy, the data graph matches that of which is usually accepted in the way that it's formatted and its shape. So what if? What if the resistivity of the conductor were reduced as close as possible to 0? How will the dynamics of the falling magnet change? The current would increase, so the magnetic field would increase, so the magnet will fall slower. And then what if holes or slots were cut into the tube? How will this affect the ring currents in your model? The current would decrease, so the magnetic field decreases, and so the magnet will fall faster. Then sources of error. Some sources of error that could have possibly caused the discrepancies in average falling down speeds. For example, the magnet might not have been dropped like straight. Also, human error in stopping the timer on time and like actually dropping the magnet, and the height at which the magnet was dropped might not be the same for each drop. Thank you.